On the south bank of the Thames, next to London Bridge, construction of Europe's tallest building is underway. But a mile south of the Shard, in Elephant and Castle, another tall building has already made a striking impact on London's skyline. Built by Brookfield Europe to a design by BFLS architects, the 43-storey Strata SE1 is London's tallest residential tower. But its height is not its defining feature. In this programme, we are going to look at the concept, design, installation and performance of Strata SE1's wind turbines.
The client's brief was quite clearly to create an object, a benchmark for urban living. It was going to be the first catalyst for to mark the start of the Elephant and Castle Regeneration Master Plan, and as such they wanted it to meet Brookfield's sustainable criteria, but also the planning policy. The GLA stipulated that you had to generate 10% on-site renewables for all new major schemes in London, and that was the key thing that set off most of the building's sustainable criteria. PVs were discounted because at the time they weren't commercially viable in comparison to the wind turbines. The surface area of PVs that we would have to have allowed for would have taken up pretty much the entire southern elevation, given that you couldn't run them floor to ceiling because obviously you've got the windows. You would have ended up with a brise soleil that would have extended all the way down the back of the building, the south elevation. You would have had to keep them clean, so the facade cleaning regime would have been more frequent, therefore it would have a direct impact on the service charge of the tenants, and they had about a 15-year lifespan. Ground source heat pumps or geothermal energy, again we had a very small site footprint to actually get the two ends of the loop effectively far enough apart was one thing, and the second thing is that the energy you save in using that type of system you expend through pumping the water to the height of the building, so it tended to cancel itself out. With that, on that basis, turbines started to present themselves as a viable option towards achieving this 10% renewable criteria.
Once we'd looked at the different options that were available for renewable technologies, we chose to go down the wind route. There was a number of interesting factors that everything started pointing towards wind. One, the speed of wind actually increases exponentially as you get up in height. So remember, we're 150 metres in the air. So the wind speed is like 5 times more here than it is at ground level. Okay. The other interesting thing was that if you take the windrows for London, the majority of wind comes from the southwesterly direction. Now, as it would happen, that curve at the back of the building that I've just shown you, along here, faces due southwest. So the whole back of the building acted like a sail, and it trapped the wind, and when the wind hits that sail, it pushes down and up. So it's actually getting channeled up towards the top of the building as well.
In the early meetings, we were just looking at ways in which we can use renewable energy, looking at all the options. One option, I remember sort of the very moment almost, the idea of the turbine was born. I was sitting next to the architect and he was sort of sketching away and just drew this huge sort of turbine at the top of the building and just sort of raised his eyebrows at me to say, can we do that? And without any analysis or anything like that, I just nodded, I'm sure we can make that work, and that's how it was born. And we went from there, really.
The key thing was to incorporate the turbines within the fabric of the building. We didn't. It became tokenism, if you like, to just plot them on top. There are other examples of where that had happened elsewhere in the Elephant and Castle, and basically we wanted to adopt them as part of a motif of the building.
Each of the 3 9-metre diameter turbines is a horizontally mounted propeller consisting of a heavy steel and concrete inertia base. Anchored to the base is a 500mm diameter, 6mm thick steel mast that is tilted 12.5 degrees forward to ensure the blade tips can't hit the mast. And fixed to the mast is the nacelle. The nacelle houses the turbine's generator, its gear, the braking systems, and all the couplings and cables. And finally, the hub, which houses the main shaft and bearings and the blade mounts for 5 blades. But why 3 turbines?
The reason we have 3 turbines at the top of the building is 2 factors. One, as I explained earlier, the overall height of the building had been dictated by this view. Okay? The quantum of floor space had been dictated by the client. That left us with a space between here and here from which to put the turbines in. Okay? It's true to say that the output of turbines is exponential as well. The bigger the diameter, the greater the output, so there's an exponential curve on that. And we could have had one 15-metre diameter turbine and we would have got the same output as the 3 turbines here, but we were sandwiching what we could in between 2 defined criteria. That's where we ended up with 27 metres of turbine.
We tested the performance of the available wind energy by using CFD, that's computational fluid dynamics. That's sophisticated computer modelling to look at the airflow regimes around the building and the additional air velocity that went actually through the turbine areas. The turbine areas are actually 9-metre diameter, but we've got a Venturi type effect by smoothing the entry points slightly on each of the turbines themselves, so they essentially capture and smooth the air through and accelerate across the turbine blades, therefore improving the performance and efficiency.
In fluid dynamics, a Venturi effect occurs when flows are constricted. At the point of constriction, the pressure differential causes a rise in velocity of the fluid. This is what was envisaged would happen in the tubes housing the rotors, but at Strata, the top of the building is sliced off, and the turbine tubes are too short to generate a true Venturi effect.
Through testing, it was found that 5 blades, as opposed to 3 or 4, was the best performance in terms of lowest noise and the most efficient generator as well. There's a balance always between noise, efficiency, peak performance and cost. 5 blades will clearly cost more than having 3, but then the other issues need to be weighed up as well.
One of the issues was what happens if the blades break and come off. If you've got a wind farm out in the middle of a moor, then that's not highly populated moor, and that's one thing. If you've got a load of people around, that's another. That was looked at very seriously, clearly, and that's resolved by having a steel strand down the centre of the blade, so that if the blade was to fail, then it's actually held in position. And there are all sorts of vibration monitors in the turbine itself as well, which identify if there's a problem, and brakes go on. There's at least an electric brake and a disc brake, so that the whole thing can be stopped fairly quickly if there's any sort of issue.
There is noise. We have an advantage that we have enclosed them within the Venturi-like enclosures. That tends to basically contain the noise into 2 sound cones, one that projects to the north of the building, one that projects to the south. If you've got a conventional wind turbine on a sort of wind farm, the noise would emanate spherically. Basically, each wind turbine sits on a inertia base, akin to putting a concrete block in the bottom of a washing machine. It dampens the movement. So that inertia base is anchored to the structural slab. It's separated vibration-wise through a series of inertia pads that are adjustable. And basically every sort of safety factor of 10 was built into it, so that whatever the acoustic eventuality was likely to be, we then designed for sort of 10 above that.
The inertia base is built out of 2 big troughs, steel troughs at the base of the turbine structure, which you then fill with concrete. So it's lighter to erect to begin with, but the very simple and quite clever bit about it is that you can then add more concrete as you need to tune out some of the vibrations. So you can have 450 thickness of concrete, and if that hasn't quite tuned it right, you can add a little bit more concrete, and so on. Very, very simple, but very effective.
This little model here is a model that we used initially to describe to the client and to all the other parties involved in this design how we'd actually build this thing. Because obviously nobody had done this before, and by seeing a 3-dimensional model you can actually understand, I'm beginning to understand how this whole thing comes together. I mean, initially when you show sketches, they say that's fine, but how do we actually build it? So if you look at this model in detail, it has all the relevant component parts of the turbines and all their components, the Venturi-like enclosure, that steelwork, and all the steelwork for the overall top of the building round here. And you can see it as it stages from the concrete floor. Everything from here on up is steelwork. Moving over to here, how we actually clad both the building and the Venturis with all the access points required, because this is a highly maintainable piece of kit.
Well, it's a challenge building anywhere in London, mainly because of the congestion. You've got to take into consideration peak traffic flows, how you're going to get people and deliveries on and off site. I mean, London is a challenging place to build no matter what size of the building and whether it's got turbines in it or not. This site presented some significant challenges in that it is a very small footprint. We are exactly 3 metres off a major Network Rail viaduct. We're 43 stories above that, so we presented a fairly significant risk to that Network Rail asset. So we had to have a very good understanding at least 14 weeks in advance of doing anything here on site so that we could gain approval through Network Rail to do basically any type of build work. So that in itself was a challenge. And I think because we are 43 floors, and it's not that common in London to have 43 floors, choosing your vertical transportation and positioning of that vertical transportation is a key to the success of the building. So it's how you get men and materials up and down site without any impediment to the progress of the build.
We had cumulative tolerance between the structural slab, the facade manufacturer, the turbine manufacturer, the Venturi manufacturer, all added together, and basically having to take these 9-metre diameter sort of moving parts and making sure they didn't clash with anything else. So as a coordination exercise, it was particularly onerous. The principles, once they're bedded in, are quite straightforward, but the actual realities of building it out are quite complicated.
It was definitely a coordination dilemma, which we eventually overcame by deciding to put all the steelwork and the secondary steelwork, fabricate it, and then install it as if we were 150 metres in the air, but on the ground on an empty airstrip. And we basically placed a mobile crane where the tower crane would be, and we all pretended we were 150 metres in the air. So we were sitting on the ground, but all wearing harnesses. So that in itself allowed us to bring the steelwork, which would eventually house the turbines, to site with an air of confidence that we could install it, and moreover, install it safely.
When wind speeds reach 6 metres per second, 2.1 kilowatts of electricity is generated. Peak performance occurs when speeds hit between 14 to 19 metres per second, at which point each turbine generates slightly more than 18 kilowatts. However, the turbines rarely turn for prolonged periods of time, not least because the blades are not multi-directional. They can only rotate when the prevailing wind is southwesterly. And even when the wind is southwesterly, for safety reasons, the blades are designed to act as brakes and to stop turning when wind speeds reach 20 metres per second. Furthermore, when access to the roof is required for cleaning and maintenance, the turbines are automatically shut off. Even with these significant restrictions, it is calculated that the turbine should generate 50 megawatt hours of electricity every year.
Because we can't store wind energy easily, we use whatever is produced immediately. There's no special requirement for plant, it's just an interface module that synchronises the electricity generated from the generator in the nacelle and then feeds it back into the building grid.
I think the thing was for us, it suited the criteria that was of the time, the 10% renewables. This contributes conservatively 8%, but don't forget that's 8% of them running 24 hours a day, 7 days a week. And because it's wind, that's not going to be the case. Brookfield and ourselves have treated this more as an experiment, if you like, wearing your heart on your sleeve, if you like, sustainability heart on your sleeve, and sort of saying that we're not going to commit to what they are going to do. What they are doing is they've partnered up with Southwark University. They're basically taking weekly readings of the turbine output, comparing that against the weather reports, and in 2 years' time they're going to look to publish a white paper that actually says these are the results that we've actually collated from these wind turbines that will either prove or disprove the appropriateness of urban wind turbines.
Probably the hardest thing with the turbines is because no one had done it before, no one had built them into the fabric of a building. I couldn't pick up the phone and say, listen, when you were doing those turbines in that roof, what did you do when this happened? So I think that was a difficult scenario for us. It was more like design on the run. So we'd get a little bit further, our design team would get a little bit further, but we couldn't take it to the point of fruition as far as design until we had engaged a turbine company. And obviously, because it's the crown of the building, it is not high on the priority when you're trying to get the frame up. So it was definitely a challenge for the design team.
The building isn't all about the turbines, it never has been. Buildings are complicated things that take in a whole number of different components to actually make the overall end product. This is one component. If we wanted to build a building or build the most efficient wind turbine, we wouldn't have had a 43-storey residential tower underneath it. We would have built it somewhere else entirely. The whole thing would have been an engineering project, not an architectural project, and it would have actually then sort of given you the most economic wind turbine in the world, but there wouldn't have been 408 apartments underneath it.